Hello, IB scholars. Welcome back to IB 360, your one-stop solution for mastering IB past papers. Today we are diving deep into IBHL Math AA Paper 1 from November 2023. So let's grab your pens, papers, and conquer these problems together. So here's our first problem. Your function g is defined by this thing, gx equals e to the power of x squared plus 1. We have to find out g dash 1. So first we'll differentiate the function. So g dash x will be, here we have to apply chain rule. In the chain rule, first we will be differentiating this function and then we'll multiply with the differentiation of the inner function. The outer function is e to the power x, so differentiation of e to the power x will remain the same. And we now have to differentiate the inner function, which is x squared plus 1. So if I differentiate x squared plus 1, it will become 2x e to the power of x squared plus 1. This thing is g dash x. Now we have to find out g dash 1, g dash minus 1. G dash minus 1 will be 2 times minus 1 to the power of minus 1 whole square plus 1. That is minus 2 e to the power of 1 plus 1 will be 2. So minus 2 e square would be the answer to the first question. Moving on to question 2. First we have to consider a circle with diameter EB. So they are talking about this circle here. And A has a coordinates of 1, 4, 0. B has a coordinates of minus 3, 2 and minus 4. First we have to find the coordinates of the center of the circle. Center of the circle is basically the midpoint of the diameter, right? So yeah, for A1, let's say this point is O. Coordinates of O would be yeah, we just have to add the A and B coordinates and divide them by 2. So we start with the x1. A has 1, B has minus 3. Minus 1 minus 3 by 2, comma the y coordinate will be 4 plus 2 by 2. And the z coordinate will be 0 minus 4 by 2. If I simplify this, the coordinates of O would be, let me write it like this. Yeah, this would be minus 1, comma 3, comma minus 2. So that will be the coordinate of the midpoint of the circle. Now for the radius of the circle, I need to just use distance formula and find the distance between O and B. So OB would be equal to root under. So there is the coordinates of O. The coordinates of B is minus 3, 2, minus 4, right? Yeah. So minus 1, minus of minus 3 will be plus 3 whole square, 3 minus 2 whole square, plus minus 2, minus of minus 4 will be plus 4. If I simplify this, it will become minus 1 plus 3 would be 2, 2 square plus 1 square plus 2 square. It will be 4 plus 1 plus 4. That is root 9. So OB is 3. So radius of this circle is basically 3. This is the answer to A2. Now A3 is we have to find the exact volume of the cone. So volume of a cone is 1/3 pi r square h. Okay, we know the radius. We have found the radius from the previous part. Now I need to find the height. So first I'll apply distance formula to calculate the value of OB, which is the height. The third B would be root under. It is minus 1 comma minus 1 comma 0. So O is here. So minus 1, minus of minus 1 will be plus 1 whole square plus 3. Again minus 1 will be plus 1 plus minus 2, and the last one is 0, so minus 2 minus 0 whole square. So if I simplify this, I should be getting 4 square plus again this will be 2 square. Okay, so that is root 20. Root 20 is basically 2 root 5. That is the height. Therefore volume would be equal to 1/3 pi r square h. So 1 by 3 pi r would be 3, so 3 square times h would be 2 root 5. So it will be 6 pi root 5. This will be the volume of this cone. As it's paper 1, we won't be able to use the calculator and find the exact value. So we'll have to keep the answer like this. So that is all about question 2. Now for question 3, in the first part we have a proof. So we have to prove this thing. So for this we can use the LHS equals RHS approach. And yeah, what we will be doing is we'll be simplifying the left hand side, and then we'll check if it's equal to the right hand side or not. So we can now simplify a square minus 1 by 2, so the denominator will become 4. A square minus 1 whole square will be a to the power 4 minus 2a square plus 1. Now I can take the a square inside the fraction, so it will be 4, denominator will be 4, it will be 4a square plus a to the power of 4 minus 2a square plus 1. Simplifying, I'll get e to the power of 4 plus 2a square plus 1 divided by 4. So here I can actually convert the numerator to a whole square, that is a square divided by 2 times a square times 1 plus 1 by 4, or plus 1 square by 4. This makes a numerator a square plus 1 whole square by 2 square, so which is a square plus 1 by 2 whole square. So this is equal to the right hand side, and hence we can say that the part A is verified. Now for part B, we have a right angle triangle with the side a square minus 1 by 2 and a square plus 1 by 2, right? Now we can apply the Pythagoras theorem. So the Pythagoras theorem says that a square plus b square equals c square. So yeah, so if you have a right angle triangle, so if these are the three sides, so a square plus b square equals c square, where c is the hypotenuse or c is the longest side. Now here from this formula we can see that the longest side is basically your a square plus 1 divided by 2, because squaring and adding a square and a square minus 1 by 2 gives you the third side. So I can say from part a square plus 1 by 2 is our hypotenuse. So if I want to draw the triangle now, it should look like this. The hypotenuse will be a square plus 1 by 2. Let's say the height is a, there's a 90-degree height is a, and the base will be a square minus 1 by 2. So area of this triangle will be half base times height. So the base is a square minus 1 by 2 and the height is a. Upon simplification, I'll get a cube minus a by 4. So this is the answer to part B. Now moving on to the next question. The derivative of a function f is given by f dash x equals 6x by x square plus 1. The graph of y equals fx passes through the point 1 comma 5. And we have to find the expression of fx. So basically this is an integration problem, right? So yeah, the f dash x is given as 6x by x square plus 1. So f dash x can be written as dy by dx. Like if we say that y is equal to fx, so yeah, it's equal to 6x divided by x square plus 1. To find y in terms of x, we have to integrate both sides. So I can transfer the x to the other side. Transfer the dx to the other side and integrate the left side, it becomes y, and the right side is 6x dx divided by x square plus 1. Now to solve this integration, we have to use the method of substitution. And what we can substitute is x square plus 1 as t. So your 2x dx will become your dt. Now from the numerator we can take a 3 common, so 2x, so the numerator becomes 2x dx, denominator becomes x square plus 1. Now this 2x dx can be replaced with dt, and x square plus 1 can be replaced with a t. So integral of dt over t can be written as y equals 3 ln mod t plus c. And yeah, now I have to solve for the constant c. So it's given that at I'll now also replace t with the initial equation, that is t equals x square plus 1. So I'll substitute back the x in the equation. Now we have a y equals fx function, so at x equals 1 your value of y is 5. So I'll plug in x equals y and 1 and y equals 5 in this equation and try to solve for c. So yeah, so c will become 3 ln 5 minus 3 ln 2. Now if I substitute the c back in the original equation, our equation will be y equals 3 ln of x square plus 1 plus 5 minus 3 ln 2. Now I can take out the 3 common, and it will become ln of mod x square plus 1 minus ln of 2 plus 5. So this can be written as 3 times ln mod ln of x square plus 1 by 2 plus 1 divided by 2 plus 5. This is y, and this is our final answer to question 4. Now in question 5, we have an equation. Here z belongs to c and p belongs to a real number r. 3 of the roots of the equation are given to us, and by considering the product of all the roots of the equation, find the value of alpha. So what are the roots? So one of the roots is alpha, other root is alpha square. 3 plus I is one root. Now thing is, if you have a complex number as a root of an equation, the conjugate of this complex number will also be a root of the same equation. So I can say that 3 minus I will also be a root of the same equation. Okay, so these will be your roots. Now we have to consider the product of all the roots and find the value of alpha. So yeah, product of roots is given by this equation, minus 1 whole to the power of n, a naught by an. A naught is the last term, an is the coefficient of the first term. Well, n is the order of the equation. So it will be minus 1 to the power of 4, a naught is 80, an is 1. The product of the root will be equal to 80. Now let's plug in the values, right? So alpha times alpha square times 3 plus I, 3 minus I. These will be the product of the root, so it's alpha cube. 3 plus I, 3 minus I will be 3 minus of I square, minus of 3 square minus I square. 3 square minus I square is like 9 plus 1. So alpha cube equals 80 by 10. So I can write as alpha cube equals 8. So if alpha cube is equal to 8, then the value of alpha, so 8 can also be written as 2 cube. So alpha will be equal to 2. So yeah, that's the answer to part A. You have to find the value of alpha, and we have found that successfully. Now the value of P. How will I find the value of P? Basically, alpha is the root of this equation. So I can directly plug in alpha in this equation and solve for P. So 2 is the root of this equation. Therefore, plugging in alpha instead of z, P times 2 cube is 54 times 2 square minus 108 times 2 is 80. This equation should be equal to 0. Now 2 to the power 4 is 16 plus 8p plus 54 times 4 is 216 minus 216 again plus 80. These two will cancel out, so our 8p would be equal to minus 96. So from here I can say that p will be equal to minus 12, which is basically the answer to this question. Now in question 6, we have event A and B such that PA equals 0.3 and PB equals 0.8. So we have to determine the value of P of A intersection B in the case where A and B are independent. So if events A and B are independent, we can write P of A intersection B as PA times PB. This would be equal to 0.3 times 0.8 is equal to 0.24. Now part B. In part B, we have to find the minimum possible value of P of A intersection B. Now to find this thing, we can use a Venn diagram. So this is A, this is B. Right? This is PA, this is PB, and this section is P of A intersection B. So P of A union B can be written as PA plus PB minus PA intersection B. Okay, so PA union B is this part, this entire section. Now if I plug in the values of PA and PB, we finally get P of A union B as 1.1 minus P of A intersection B. Now P of A union B will have a value, of course, will have a value of less than equal to 1. It can be equal to 1, or it can be less than equal to 1. Now, yeah, I can just plug this thing here. And if I simplify this a little bit, minus 0.1, I can multiply negative on both sides. That will flip the equality sign, flip the inequality sign. So this is it. Therefore, minimum possible value of P of A intersection B is 0.1. Will be less than will be equal to 0.1 is the answer. Now the last part is what is the maximum possible value of PA intersection B. Now again this can be understood in terms of a Venn diagram. So maximum value will occur when the event A lies inside event B. So if this is B, A is here, A. So in this case P of A intersection B would be equal to PA, which is 0.3. Yeah. So this is only possible when like A lies inside B of the Venn diagram. Now moving on to the next part. Now in question 7, we have a curve x squared plus y squared times y squared equals 4x squared. The domain and range is given to you, x greater than or equal to 0 and y is in between -2 and 2. Show that the curve has no local maxima or local minima points for x greater than 0. So we can just start by opening the brackets. Now we can differentiate both sides. So it will be 2x y squared plus differentiation of y squared would be 2y dy by dx. Differentiation of y to the power 4 will be 4y cubed dy by dx equals the differentiation of 4x squared would be 8x. Just write it here. Differentiate in both sides. Yeah. Now, if you have a local maxima or local minima, at the local maxima or at the local minima, your dy by dx would be equal to 0. That is a critical point. So, local extrema, our dy over dx would be equal to 0. So we can plug this information in this equation and see what we are left with. So 2x y squared minus 8x equals 0. I can take 2x common and I'll get y squared minus 4. So from here 2x, so one of the values of x where your dy by dx will be equal to 0 will be at x equals 0. Okay. And the other possible values like in terms of y will be y squared minus 4 equals 0. So y squared equals 4. So you'll get y equals 2 and y equals minus 2. Now see, if I check the range of values of y is less than 2 and less than minus 2. So these 2 points are out of the domain of y. Domain of y. So in our curve, these 2 points will not exist. So we cannot accept the local maxima or local minima which lies on these 2 points. So yeah, we have to ignore these two. Now we have another thing we're left with x equals 0. Now we have to check that there is no local maxima for x greater than 0, not at x equals 0. X equals 0 will be a valid solution for this curve. Okay, but yeah, we have to check for x greater than 0. Therefore, x equals 0 also doesn't lie in x greater than 0. So finally I can say hence the curve has no local maxima or minima for x greater than 0. Alright, now in question number 8, let fx equals cos x minus k, where the value of x or the domain of this function is from 0 to a, and the values of a and k, they belong to a positive real number. By considering the case where k equals pi by 2, we have to find the largest value for which the inverse function exists. Okay, for a, fx will be cos x minus pi by 2. Cos x minus pi by 2 can also be written as cos pi by 2 minus x. Cos 90 minus x is obviously sin x. Now if I try to plot sin x, I mean the domain of x is greater than 0, so the curve will look like this. Okay, so this value is pi by 2, this is pi, this is 0. Now we have to find the largest value of a such that the inverse function exists, right? So for an inverse to exist, the function fx must be 1 to 1. So what is a 1 to 1 function? In a 1 to 1 function, every value of x will have a unique value of y. But in our sin x curve, we see that the curve is increasing from 0 to pi by 2, then it starts to decrease, right? So after pi by 2, you see that the values start getting repeated, or the x values. For example, the x here will have this value of y, and again the x here will have the same value of y. So after pi by 2, the values of y for x starts to repeat, and as a result, if we restrict the domain from 0 to pi by 2, then only our inverse function can exist. So for this part, your maximum value of a will be equal to pi by 2. Now moving on to part B, we have to find the largest value of a for which the inverse function exists in the case of k equals pi. So your fx is now cos x minus pi. Again be written as cos pi minus x. Cos pi minus x is basically minus cos x. So if I plot minus cos x, the function will look like this when x is greater than 0, obviously. So this is 0, this is pi by 2, this is pi. Yeah. Now again we have to check the maximum value of minus cos x, so that an inverse exists. Now we see that cos x, minus cos x starts increasing from 0, it keeps increasing until it reaches pi. After pi the function starts to decrease. So we see that after the value of x crosses pi, we have the same value of y for two different values of x. So the function doesn't remain 1 to 1 after the domain crosses x equals pi. So if we can restrict the domain up to x equals pi, then what happens is the function will become 1 to 1. And as a result our inverse will be able to exist. Therefore a equals pi. The function minus cos x increases from x belongs to 0 comma pi. After x equals pi, the function starts to repeat. The function starts to decrease. Hence, the function doesn't remain 1 on 1. So if we can restrict the function till a equals pi, then restrict the domain, then we can say that the inverse function will exist. Now moving on to part C. So you have to find the largest value if the inverse function exists, the case where k is in between pi to 2pi. This was a little difficult problem for this November 2022. So it's cos x minus k, also written as cos k minus x. Now see, what is cos k minus x? Now, the minimum value of k is pi, okay? The maximum value is 2pi. When k is equal to pi, cos pi minus x will have a graph like this, which is basically minus cos x. The graph will kind of look like this. We have already drawn this graph, right? Now, what happens is, this is cos pi minus x, right? Now, what really would happen here is, like, if you start increasing the value of k from pi towards k pi, this curve will start moving towards the right by k minus pi units. Okay, so yeah, though the curve after it moves, it will look like this. Let me try to make it better. So this point here would be k minus pi, right? So yeah. So what really happens is, see, after the function crosses this k minus pi, again the values start to repeat. So if you can restrict the domain till k minus pi, then only your inverse function can exist. You just remove this part because the domain starts from 0. So yeah, here the value of a will be k minus pi, which is the answer. Now for question 9, we have a homogeneous differential equation. So we have to solve it by substituting y equals vx. So y equals vx, if I differentiate both sides, I have to apply chain rule on the right side. So first I'll differentiate v keeping x constant, then I'll differentiate x keeping v constant. So v dx by dx is 1. So dy by dx should be replaced with x dv by dx plus v, and y should be replaced with vx in the original equation. The original equation will become x dv over dx plus v. This will be equal to y is vx, so vx whole square minus 2x square x times vx. So if I just simplify the right hand side, it will become v square x square minus 2x square divided by vx square. And again simplify the right hand side by taking out x square common from the numerator and x square common from the denominator and subtracting both of them. Now this can be further simplified. Sorry, the denominator would be v. Yeah, if I just break it into two fractions, so v square by v minus 2 by v. Basically I can write x dv by dx plus v as v square by v would be v minus 2 by v. So plus v minus v, these two will cancel out. So x dv by dx would become minus 2 by v. So v dv would be equal to minus 2 dx over x. Now if I integrate both sides, v dv will become v square over 2 and minus 2, and integral of dx over x will give me ln mod x plus c. Now if I want to replace v back, so v would be equal to y over x. I'll replace that in the final equation. So y over x whole square is y square by x square. So left hand side will become y square divided by 2x square. The right hand side is twice ln mod x plus c. Now the initial the condition is given when x equals 1, y equals 2, right? So I'll put y equal 2 and x equals 1 in the equation. So I'll get 2 square by 2 times 1 square equals minus 2 ln 1 plus c, or ln mod 1 plus c. So ln mod 1 equals 0, so this term would be 0. So c would be 2 square by 2, which is 2. So yeah, finally our differential equation becomes y square by 2x square equals minus 2 ln mod x plus 2. Now we have to report the answer in the form y square equals fx. So I can multiply the 2x square to the other side. So the right hand side is just a function of x, so our answer will be satisfied. So this will become minus 4x square ln mod x plus 4x square. This is the answer to part A. Right? Now in part B, the point of zero gradient to the curve lie on two straight line y equals mx, where m belongs to R. Find the values of m. So the gradient of this curve will become 0 when dy by dx equals 0. Just add a page here. Yeah. Is equal to 0 is same as dy by dx equals 0. So if in the initial differential equation, if I replace dy by dx with 0, I'll get something. So simplification, I'll get y square minus 2x square equals 0. So if I can factorize this thing, I'll get y plus root 2x, y minus root 2x if I factorize the left hand side. So both of these can be equal to 0. The first equation will be y plus root 2x equals 0, y minus root 2x equals 0. Left hand side will get y equals minus root 2x, and this one will become y equals plus root 2x. So the value of slope for the first one is minus root 2 and the second one is plus root 2. The value of m will be plus minus root 2 or plus root 2 and minus root 2. This is the final answer to question 9. Now in question 10, the function f is defined by fx equals cos square x minus 3 sin square x. So we have to first find the roots of fx. So fx is cos square x minus 3 sin square x. So cos square x can be replaced by 1 minus sin square x. And if I simplify this equation, I'll get 1 minus 4 sin square x. This will be equal to, this is the fx. Now I have to simplify fx. How will I do that? So to simplify fx, not simplify, we have to make fx equals 0, right? So fx equals 0. So this means your 1 minus 4 sin square x should be equal to 0. So here if I simplify, I'll get sin square x equals 1 over 4. Now the domain of this function, or domain of x, is from 0 to pi, right? And in between, so if I take a root of sin square x, I should get two values, sin x equals half or sin x equals minus half. Now from 0 to pi, sin x is always positive. The curves of sin x from 0 to pi looks like this. This is pi, this is 0. So sin x cannot be equal to minus pi. Now sin x equals, Now for question 10, the function f is defined by fx equals cos square x minus 3 sin square x. The domain of x is from 0 to pi. Now we have to find the roots of the equation fx equals 0. So we can write fx as cos square x minus 3 sin square x. Cos square x can be replaced by 1 minus sin square x. So if I simplify this, I'll get fx equals 1 minus 4 sin square x. Now we have to solve for fx equals 0. So basically we have to solve for 1 minus 4 sin square x equals 0. So here if I simplify, I'll get sin square x equals 1 by 4. So from here I'll get two solutions, sin x equals half and sin x equals minus half, right? But thing is, from in the domain 0 to pi, sin x never becomes negative. So sin x curve will look like this from 0 to pi. This is 0, this is pi by 2. Right? So sin x cannot be equal to minus half. So let's find the values of x from 0 to pi for which sin x can become half. So yeah, the first value for it becomes half is pi by 6. Sin 30 becomes half. The other value, or this value, would be so one value of x will be pi by 6. The other value of x will be pi minus pi by 6. Therefore x will be equal to pi by 6 comma 5 pi by 6. These will be the roots of the equation fx equals 0. So this will be pi minus pi by 6. This is the answer to part A. Now in part B, first we have to find f dash x. So your f dash x will become, we'll try to differentiate directly from here. Differentiation of 1 is 0. Minus 4 sin square x will be minus 4 times 2 sin x. And now we'll apply the chain rule. Differentiation of sin x is cos x. Okay. So this 2 sin x cos x will become sin 2x. So f dash x is minus 4 sin 2x. Okay. Now in part, this is B1. Now we have B2. In B2, we have to find the coordinates of the point where f dash x equals 0. Okay. F dash x equals 0 means minus 4 sin 2x would be equal to 0. So sin 2x will be equal to 0 if I cancel out the minus 4. So we have to find the solution of sin 2x equals 0 in the domain of x, which is from 0 to pi. So at x equals 0, this will be valid, sin 0 is 0. At x equals pi by 2, this will be valid. Because see, sin of 2 times pi by 2 is equal to sin pi, and sin pi is equal to 0.
right? And it will also be valid when x is equal to pi. Why? Because if x equals pi, you'll have sine 2 pi. Sine 2 pi is 0. So at these three values of x, your f dash x equals 0, but we need the coordinates of the points. Okay, so the first point, when x equals 0, I'll just put 0 here. The value of fx is 1. Okay, and the value of when the value of x is pi by 2, what is the value of fx? So I'll put pi by 2 here. So pi by sine pi by 2 is 1, so sine square pi by 2 is also 1. So 1 minus 4, this will become minus 3. So f of pi by 2 will be minus 3. And then if you put pi in this equation, sine square pi will be equal to 0, so your fx will again be 1. So these are the 3 points where your f dash x becomes 0. Now we have to sketch the graph of y equals mod fx. And yeah, so first to solve this thing, we will first plot y equals fx and then take the mod. This is the equation y equals fx. So see, the equation will start at 0 and end at pi. At x equals 0, your y will have 1. So the initial point of this equation will start at 1. Okay. So after 1, what happens is this function becomes 0 at x equals half, right? So it will become 0 at half. Yeah, this value is x equals half, right? This y equals 1. This x equals half. After that, it will keep decreasing, and it will at pi by 2 it will become minus 3. So this happens at pi by 2. X equals pi by 2. Then it starts. Then what happens is the function increases, and it has another 0 at 5 pi by 6. So this value will be 5 pi by 6. Okay, the value of x. Yeah. And no, this 1 second. Yeah, this value will be pi by 6, not half, because yeah, this solve. The first root occurs at pi by 6. So yeah, this point will be 5 pi by 6, and at the end, at x equals pi, the value of y will be 1. So yeah, it will end like this, is equal to pi. So this is the y equals 1 line, and there is a y equals 3 line. This is the curve y equals fx. Now y equals mod fx, what happens is the part which is below the y-axis, it will get reflected above, something like this. So let's try to do it. Yeah. So this will be y equals 1, this is x equals pi by 6, then the function will increase right up to this point, come down. Okay, and this point will be 5 pi by 6. This is the point of maxima. This is pi by 2. This is 0. Yeah, after that it will rise up to y equals 1, and this is pi. So this line is a y equals 1 line, and this value will be y equals 3. There's a minimum value of y equals minus 3. So if you raise this above, this point will become y equals 3. So this should be your curve. Now we'll be moving to the last part. Yeah, so we have to solve the inequality if mod fx greater than 1. Mod fx greater than 1 is, we need to find this interval, because mod fx greater than 1 only occurs in this part of the curve. So you have to find this coordinate and this coordinate. The values of x between these two coordinates will be will satisfy the inequality. Now see, in our original fx curve, these 2 points would be in the negative, right? So it will be y equals minus 1. So what we can do here is we can put fx as minus 1 and then start solving the equations for x. So I will get both the values. So if minus 1 equals 1 minus 4 sine square x, so it will be minus 2. So sine square x would be equal to half. So sin x again would be equal to only 1 by root 2, and sin x will not be equal to 1 by root 2, because sin x does not become negative from 0 to pi. Sin x equals 1 by root 2. We'll have two solutions. One is x equals pi by 4, which is 45 degrees. Another one is pi minus pi by 4. The values of x again are pi by 4, 3 pi by 4. Okay. So here, this point is pi by 4, and this point is 3 pi by 4. The values of x in between pi by 4 and 3 pi by 4 will all satisfy the inequality that mod fx is greater than 0. So here it will be. Let's check again the question in case we have it's just greater than. So yeah, this will be the answer. Now moving on to question 11. We have to consider a 3-digit code ABC, where each of the ABC is assigned one of the values 1, 2, 3, 4, 5. So first we have a permutation combination question. We have to find out the total possible codes if assuming each value can be repeated. So you have A, B and C. So you can choose any of the one numbers out of 5 for A. So A can be filled in 5 ways. Similarly, B can also be filled in 5 ways, because you can again choose any one of the 5 numbers, and also C can be filled in 5 ways. So total number of ways you can fill ABC would be 5 times 5 times 5, which is 125. So moving on to option 2, that is assuming no value is repeated. So if no value is repeated, we can fill A with any one of the numbers we like out of the 5. For B, we can't fill B with a number we have already filled A, because the numbers cannot be repeated. So B can be filled in 4 ways, and similarly 3 can be filled in 3 ways. So total number of ways would be 5 times 4 times 3, which is equal to 60. So that's all for part A. For part B, we have px, which is x cubed plus ax squared plus bx plus c, and abc is assigned one of the values of 1, 2, 3, 4, 5. We have to assume that no value is repeated. We have to consider the case where px has a factor of x squared plus 3x plus 2. First, we have to find an expression for b in terms of a. So px, which is x cubed ax squared plus bx plus c, this can be written into factors. So one of the one factor is given to us, x squared plus 3x minus plus 2. Let's say it has a degree 3, so there will be another factor, that is, let's take the factor as x minus q, right? So we can now factorize this thing, and this can be written as x squared plus 2x plus x plus 2 times x minus q. So px can be written as, if I take an x common, it will be x plus 2, take a 1 common, it will be an x plus 2, and there is x minus q. So finally px can be written as x plus 2 times x plus 1 times x minus q. From this we can say that roots of px would be x equals minus 2 and x equals minus 1. Also x equals q will be another root, but it's but still we don't know what's the value of q. Okay, so I'm ignoring the root for now. Yeah, these will be the roots. Now if I plug in minus 2 and minus 1 in this equation, we should get 0, because these are the roots. P of minus 2 is 0, P of minus 1 will also be 0. X square will be minus 2 cube. It's a times minus 2 square plus b times minus 2 plus c. We can simplify it a bit, that is minus, or we can write it like minus 8 plus 4a minus 2b plus c. This will be equal to 0. This is our first equation. Now second equation, we can plug in minus 1. So p of minus 1 would be minus 1 whole cube plus a times minus 1 whole square plus b times minus 1 plus c. Again, if I simplify, I'll get minus 1 plus a minus b plus c. This will be equal to 0. This will be our second equation. Now what we have to do is we have to find a relationship between b and b, or we have to write the expression for b in terms of a. Now to do that, what we can do is we can eliminate c from these two equations, and we'll get a relationship between b and a. So we can do 2 minus 1. Yes, that will be simpler. So minus 1 plus a minus b plus c equals 0. Minus of minus 8 plus 4a minus 2b plus c equals 0. On subtracting these two, we should get 7 minus 3a plus b equals 0. So we'll get b equals 3a minus 7. So this is the answer to the first part of b. Now we have to also show that the only way to assign the values is a4, b5, c2. In order to solve part 2, we have to make a table. So this is the values of a versus the values of b. If the value of a is 1, value of b will be minus 4. This is not valid. Why? Because the value of b can be any number between, can be any number other than 1, or b can have values from 1 to 5, but it won't have it won't be possible to plug in 1 in b, because 1 has been repeated in a. So b equals minus 4 won't be a solution. If I plug in a equals 2, I'll get the value of b as minus 1, which is also invalid, because it's not in the range from 1 to 5. If I put 3, then b becomes 2, which can be a valid solution. If I put 4 in a, I'll get 5 as b, which can again be a valid solution. And if I put 5 in a, I'll get 8 as b, which is invalid, because the range of b would be from 1 to 5. So from here we see that only 3, 2, 4, 5, these two combinations can work. But now we have to check for the values first, values of c. I'll choose the second equation. Okay. I'll do is I'll put a equals 3 and b equals 2, which is the second condition, in equation 2, and test for the value of c. So if I put a as 3 and b as 2, the value of c would become 0. Now this is invalid, because c can have values from 1 to 5. C equals 0 is an invalid solution. So the solution after testing b, 3, 2 will not be valid. Let's test a equals 4 and b equals 5. Minus 1 plus 4 minus 5 plus c equals 0. In this case we are getting c as 2. So c as 2 is a valid solution, obviously. So Yeah, so only solution here will be a equals 4, b equals 5, and c equals 2. So we have proved it. Now we have to express px as a product of linear factors. Quickly add a new page here. Yeah. So px has x equals minus 1 as a root, or x plus 1 is a factor of p. So px, so I'll try to factorize px to find the other roots. So our px would be, after plugging in abc, this px would become x cubed plus 4x squared plus 5x plus 2. So you can also divide px with this, with this thing, you'll get the answer. But I'll use a slightly different approach. I'll factorize this cubic polynomial, or this cubic equation. It will be x squared plus 3x squared plus 3x plus 2x plus 2. I'll be breaking down the equation like this. I can take out x squared as common, then I can take out 3x as common, and I can take out 2 as common. Then I'll take out x plus 1 as common. X squared plus 3x plus 2 can be factorized as x squared plus 2x plus x plus 2. So we will get x plus 1 times x plus 1 times x plus 2. So px can be written as x plus 1 whole square times x plus 2. This is the answer to part 3. Now moving on, we have to sketch the graph of y equals px, clearly showing the intercept with any axis. So let's try to draw the sign scheme of px, or the sign diagram. In a sign diagram, we'll plot the roots. So if I test with a value less than minus 2, let's say minus 5, what happens? This px will become negative, because minus 5 plus 2. So we can see minus 5 plus 1 whole square times minus 5 plus 2. This thing will become 16, and this thing will become minus 3, so this becomes minus 48. This entire thing would be negative. So value of px beyond minus 2 would be negative. Between minus 2 and minus 1, let's say we plug in minus 1.5, right? So minus 1.5 plus 1 whole square times 2 minus 1.5. This will be a minus 0.5 whole square times 0.5. So if you check, as you are squaring this negative, the negative will get removed and you'll get 0.5 whole cube. So this part will become positive. Now if I put a value greater than minus 1, let's say 0, so 0, 0, you'll see 1 square times 2, which is obviously a positive number. Yeah, there's a sign diagram of px. Now let's try to plot this. And two things here. When x tends to infinity, your px will also tend to infinity. When x tends to minus infinity, your px tends to minus infinity. Okay, you can replace x with infinity and minus infinity and derive this thing. Now we'll try to plot the curve. This is minus 2, this is minus 1. The curve will start increasing from minus infinity to minus 2. It'll reach a maxima here, then start decreasing to minus 1, and then start increasing again. Now here, this is approximately how the curve will look like. It doesn't look a little smooth, but yeah, this should be fine. And we have to show the intercept with the axis. So the x-intercepts are shown here. We have to find the y-intercept. So what's the value of y when x equals 0? So if I put x equals 0 in px, I'll get the value of p of 0 as 2. So this intercept would be 2. So that is the overall curve here. We see that the local minima of this curve occurs at minus 1, and the local maximum will be somewhere between minus 2 and minus 1, which we can derive using calculus, but it's not required in this question. So this will be the answer to question 11. So coming to the last question. So Zn is a complex number that is defined as Zn equals n square plus n plus 1 plus I for n belongs to natural numbers. So we have to find the value of argument of Z0. So Z0 would be basically 0 square plus 0 plus 1 plus I, which is I plus 1 plus I. So our argument of Z0, as you know, both the imaginary part and the real part are greater than 0. So this complex number lies in the first quadrant. For the first quadrant, your argument would be the imaginary part, coefficient of the imaginary part divided by the coefficient of the real part. So it's tan inverse 1, which is pi by 4. Now for part 2, we have to write an expression for arc Zn in terms of n. So, sorry for that, yeah. So Zn is basically your n square plus n plus 1 plus I. Okay. Now, n square plus n plus 1 is positive, while the coefficient of the imaginary part is also positive. So again, this will lie in the first quadrant. So if it lies on the first quadrant, then your argument of Zn would be basically tan inverse coefficient of the imaginary part divided by the coefficient of the real part. So this will be the answer. So with this, our part A, question A, 1 and 2 are done. We'll start with B now. So B1 we have to like show that tan inverse or arc tan A plus arc tan B is arc tan A plus B by 1 minus AB. So let's Y be equal to arc tan is also the same as tan inverse. So tan inverse A plus tan inverse B. Now we can take tan on both sides. Now, so basically these are two angles A and B, and we know that tan of A plus B can be written as tan A plus tan B 1 minus tan A tan B. So applying the same formula here, we'll get tan of tan inverse A is tan of tan inverse B divided by 1 minus tan of tan inverse A tan of tan inverse B. Simplify this. Tan of tan inverse A will be A, tan of tan inverse B will be B, and again this will be A times B. So tan Y would be A plus B, so Y would be tan inverse of A plus B by 1 minus AB. So hence we have proved that therefore tan inverse A plus tan inverse B is equal to tan inverse A plus B by 1 minus AB. Hence we have proved. So B1 is done. Now B2 is we have to show that our argument of W1 is tan inverse 2. So W1 would be Z0 times Z1. So argument of W1 would be argument of Z0 Z1. Now argument, if you have like from the properties of argument, we know that argument Z0 times Z1 can be written as arg Z0 plus arg Z1. So Z0 is 1 plus I and Z1 is 3 plus I. Or did I get that? Z0, I'll put n equals 0 here, I'll get 1 plus I, and I'll put n equals 1 here, 1, 1, so it will become 3 plus I. So Z0 is I 1 plus I, and Z0 is 1 plus I, and Z1 is 3 plus I. So this one would be tan inverse 1 by 1, and this one will be tan inverse imaginary part divided by real part. So tan inverse 1 plus tan inverse 1 over 3. Now tan inverse A plus tan inverse B can be written in this formula. Tan inverse 1 plus 1 by 3 divided by 1 minus 1 times 1 by 3. Numerator will become 4 over 3. The denominator will become 2 over 3. So this thing upon simplification will become tan inverse 2. Therefore, we have proved that argument of W1 is tan inverse 2. Now we are also done with the part B. Now in part C, we have to prove by mathematical induction that arc Wn is basically equal to arc tan inverse 1. So for mathematical induction, we have to first check whether this relation is valid at n equals 0. Then we will assume that the relation is valid at n equals k. And then we have to prove that the relation is valid for n equals k plus 1. So we start part C. So our relation is arc Wn, or I guess it's W or omega. Yes, W. This will be equal to arc tan n plus 1. We have to prove this, or we have to prove this is equal to tan inverse n plus 1. Okay, so we'll start with n equals 0. So for n equals 0, your LHS would be arg W0. W0 is basically equal to Z0. Z0 is basically 1 plus I. That is tan inverse of 1. The LHS becomes tan inverse 1. Now RHS, if I put n equals 0, it will become tan inverse 0 plus 1. That is tan inverse 1. Therefore, your LHS is equal to RHS for n equals 0. Hence, I can see that this relationship, this relation is true for n equals 0. Now we'll assume that this relation is true for n equals k. Assume the relation to be true for n equals k. So what happens is we'll assume that arc Wk is equal to tan inverse k plus 1. We will assume this. Now we have to check whether it's true for n equals k plus 1. LHS would be arc Wk plus 1 is basically arc Wk plus arc Zk plus 1. Right? Because see, Zk plus 1 means what? Omega 1, the W value will be Z0, Z1 up to Zk. This was Zk, right? And Wk plus 1 would be the same thing, Z0, Z1 zk, and you have the extra term that k plus 1. So k plus 1 can be written as wk times z times k plus 1. So this thing we can plug it here. I mean, we can add another step, which is it will be equal to wk times z k plus 1. Then from the argument properties, we can separate these out. So our wk, we already have taken this assumption that it's true, so it will be k plus 1, and arg z k plus 1. So z k plus 1 is which number? I'll place k plus 1 instead of n in this equation. It will be this k plus 1 plus 1 plus I. This is the complex number z k plus 1. Now I have to find the argument of this thing, which is basically the imaginary part divided by real part. So I can basically write it like this 1, right? So now tan inverse e plus tan inverse b can be written as tan inverse e plus b. I'll try to open the bracket here. This k plus 2 1 minus ab k plus 1 times so it's going to be a long calculation, but yeah, you all have to bear with me. So this thing will be k square plus 3k plus 3, and this will be k plus 1 divided by k square plus 3k plus 3. So if I simplify this further, I'll get k plus 1 times k square plus 3k plus 3. This one divided by k square plus 3k plus 3. There's a numerator part, so the denominator part will be k square plus 3k plus 3 minus k plus 1 divided by k square plus 3k plus 3. Now we can cancel these two out. I would need a more page here. So yeah, if I again simplify this, the numerator will become k square plus k cube plus 3k square plus 3k plus k square plus 3k plus 3 plus 1. And the denominator, if I simplify, it will become k square plus 2k plus 2. Now I'll simplify the numerator further. It will become k cube plus 4k square plus 6k plus 4 divided by k square plus 2k plus 2. So this is the tan inverse value. Right? Now, we can try to factorize the numerator part. So we see that k equals minus 2 will be a root of the numerator. So we can use it to factorize. So k cube plus 2k square plus 2k square plus 4k plus 2k plus 4, 2k plus 2. Tan inverse k square k plus 2 plus 2k, k plus 2 plus 2, k plus 2, k square plus 2k plus 2. Or it will be tan inverse. I can take k plus 2 common. The rest of the stuff will be k square plus 2k plus 2. The denominator is also k square plus 2k plus 2. So these two will cancel out. So finally, I'll have tan inverse of k plus 2. So tan inverse of k plus 2, this is our LHS. The RHS would be tan inverse of k plus 1 plus 1, which is equal to tan inverse of k plus 2. So here also we see that our LHS is equal to RHS. Hence, this relation is true for n equals k plus 1. So as the relation is true for, just write it here, is true for n equals 0, n equals k plus 1 is true. Hence, this treatment is true for all n belongs to n by induction. And with this, we are done with the paper 1, and I'll soon be posting the solutions of paper 2 and paper 3. Thank you so much.